Hello, students. Today we are talking about circles more, and we're in this topic, and there are 5 sections, and we did some arcs and sectors and some tangent lines. Today we're talking about chords, and then we have inscribed angles, which are really important. We'll spend 2 days on that, and then secant lines and segments. So today's topic is chords. What is a chord? A chord is a segment whose endpoints are on a circle. So I can have a line segment whose endpoints are on a circle. Here's a point, and here's another point. I can name those points. I can name this one A, and this one B. And if I wanted it to be a chord, I would connect A and B with a line segment like that. So line segment AB is a chord. We would write that as chord AB. You could also say line segment AB. Or if you see this and you know it's on a circle, you could say, I'm looking at chord AB. So there's a few options for that. Let's look at some other chords. So I can just choose any 2 points on the circle. What if I go closer to the edge of the circle? What happens to the length of the chord? The closer I get to the edge of the circle, the smaller that chord gets, right? So chord AB is a little bit longer, and this one's a little bit shorter. I could call this DE. What do you think a name for the chord that has the longest, where's the longest chord in the circle? How can I get it super long? The chord of longest length has a special name. And if it goes straight through that center point, we'll assume that that's the center. What is that chord called? I'm going to call it FG. The chord of longest length. The chord of longest length is a diameter. Is a diameter. And there's more than one, but the longest chord you can get in the circle goes through the center of the circle. So in this case, it's diameter FG is the longest chord. And you can kind of see the closer the chord gets to the edge of the circle, the shorter it gets. And then it gets bigger, 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 super big. Once it goes across to the other side, it starts to get small again. Here's a figure. What do you notice? What do we see? What can we do with this figure? Okay, good. I see a chord. I see, how many chords do you see? I see chord SR. What else do we notice and see? Yeah, I see a chord that's a diameter. Chord SU is a diameter. It's a chord that's the longest. Is there another diameter in this problem? SU goes through the center and has endpoints on both. What about RT? Yeah, also a diameter. Chord RT is a diameter. Circles have an infinite number of diameters, but they're all the same measure. What else? Do we see another chord? Yep, I see another one. Where's another chord? Chord TU. From there to there, that's a chord. How about radii? Do you guys see any radii? Yeah. QS is a radii. What else? Good. QT. What else? Good. QU and QR. All of those are radii. It's kind of interesting. Someone said in class the center of the circle is Q. We know that that's true. Good. So what do we think is true about this situation? Is there anything that we can mark in our figure? If all of these are radii, aren't they all the same? Mm-hmm. And what are these two angles? What's the relationship between this angle and this angle? What are those called? They're vertical angles. Okay, does anyone see it yet? What do we know about the triangles? Do you see the two triangles? They're isosceles, that's right. SQR is congruent to triangle TQU. Why? Put it all together. What is it? Side, angle, side. So why are the triangles congruent? Because of side angle, side, triangle congruence theorem. So I'm going to put an exclamation point on it. Side angle, side. So if the two triangles are congruent, what's that tell us about the chords? Okay, in this problem, we are allowed to say that chord SR is congruent to chord SR is congruent to chord TU because the triangles are congruent, so corresponding parts of congruent triangles are congruent. Corresponding parts of congruent triangles are congruent. Someone in class also said that they're parallel. Do they look parallel? They are parallel. Bonus fact. Chord SR is parallel to chord TU. You can prove that by showing that these angles are congruent, and then because they are alternate interior, the lines have to be parallel. So there's a lot going on in this picture. You could also say that SU and RT are congruent because they're the same. They're both diameters. Kind of fun to engage in a problem like this. And you can see it all comes together. Side angle, side, corresponding parts of congruent triangles are congruent. All of this comes together. Vertical angles. All right, in this section, there's a lot of statements that you can make about chords in a circle. So if two chords in a circle are congruent, I'm going to get rid of this, then their central angles are congruent. What does that mean? Two chords in a circle are congruent, then their central angles are congruent. So I'm just going to start by drawing two chords that look about the same to me. So I'm going to go from there. We'll go chord FA, chord FA. Kind of close to the edge of the circle, so it's a lot shorter than a diameter. And I'm going to say we want two chords in a circle that are congruent. So I'll do one over here. Kind of the same distance out here. Maybe that looks about right. Does that look congruent to you? It might be a little bit of an optical. I might make it a little longer. It's easy to have an optical illusion here. Oops. Make it a little bit longer. So this says if two chords are congruent, I'll call this DQ, Dairy Queen. All right, if two chords are congruent, so if chord FA is congruent to chord DQ, then this theorem says that what? I'm going to change colors. We need the center of the circle is here. So what's a central angle? A central angle, we'll call this circle C. A central angle is an angle whose vertex is on the center. Okay, so this would be the central angle right here. And there's another central angle over here. Okay, and what this theorem says is that if these chords are the same length, if they're congruent, then the chords are the same, sorry, the angles, the central angles are the same amount of the circle. And that kind of makes sense because it's taking up this much of the circle. And this one is also taking up that much of the circle. So the way this theorem would be written is then angle FCA is congruent to angle DCQ. DCQ. That's what that theorem says. Now, the converse is also true. And we could prove these, but we're not going to right now. Does anyone think they know what the converse would say? So we have if two chords on a circle are congruent, then the angles are congruent. So what's the converse? If two, what kind of angles are these? Central. Two central angles are congruent, then the chords are congruent. Let's just keep it that way. So you can do it, you can work this thing backwards. So if you know that two chords are congruent, you know the central angles are congruent. If you know the central angles are the same, then you know the chords are the same. Let's look at another one. So here's another statement that someone thinks is true about circles, and it is. I'm going to get rid of this again. This it's interesting, but I don't have time to talk about that. So what do we have? If two arcs in a circle are congruent, then their chords are congruent. Okay, so what does that mean? Let's do an arc. This is the arc. And should we name the arc? We can name it JK. And we can name this one, we want an arc that looks like the same amount of the circle. So I don't know, that looks about right. If I want to force it, I can say this one is about 85 degrees, a little bit less than 90 maybe. And this one is about 85 degrees, more or less. We'll say that they are the same. And then, so that's what we're starting with. We're starting with if two arcs in a circle, if two arcs in a circle are congruent. So if arc HI is congruent to arc JK, then what's true? Then what are we allowed to say? We're allowed to say that the chords are congruent. Does that make sense? Then chord HI is also congruent to chord JK. That's just another way to say, if you have that much of the circle around the edge, that means that these are going to be the same. Anyone want to try the converse? Okay. If two chords are congruent, then their arcs are congruent. Something like that. So it works both ways. It's basically this is how much of the circle you have. And if these numbers are the same, then these numbers are also the same. So if this was 5, this would also have to be 5. If it was 24, this would also have to be 24. Ooh, let's do a math problem. So here's circle P, and we want to know something about circle P. So let's engage with the problem a little bit. So we know that the measure of arc AB is 43. I'm going to put that right into my picture. Okay, and we also know that AC, this chord, is the same as chord DF. So if we can find out how long AC is, then we know how long DF is. And what this says is find DF. Okay, and what that means is I don't want the measure of arc DF. I don't want DF this way. I want the length of DF. So if it says find DF, I want to know what is the length of chord DF. That's what that means. I don't want the measure of the arc. I want the length of the chord DF. I don't want the measure of arc DF. That's different. Okay, so how long is it? Well, I haven't taught you everything here, but if this is 2, this kind of looks like 2 to me. So how long is AC? That looks like 4. So how long is DF? 4. DF equals 4. And you have to work these pictures, play with them, mark them up, see what you know. You do have to understand what the question's asking you. So if it's just 2 letters, we want the length of a line segment. Here's another problem. What is if chords, oh, I like this one. If chords are equidistant from the center of a circle, then they are congruent. Okay, this one is, if you've been paying attention, should make sense to you. So I'm gonna have I'm gonna start with a radius, and I'm gonna pretend like this circle has a radius of 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. I'm doing it kind of weird, but this is 1, 2, 3, 4, 5. If I have a radius over here, radiuses are going to be the same length, assuming I got the center in the right spot. And I could also mark that out. 1, 2, 3. Uh-oh. Wow, it's a little bit of an optical illusion. All right, let's try a little bit. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, so I have some radii that are marked off. If I go 2 units away, right here, so I just said that this is 2. And if I go 2 units out on this radius, we're going to make that also 2. Okay, I went the same distance on both radii. Now, if I have chords that are intersecting those points, I'm going to call this circle C. I'm going to call 2 units away, I'll call that B. And I'll call 2 units away here A. I'm so creative. All right, now if I have a chord going through B that's perpendicular, that's has to be perpendicular. That's not perpendicular. So I have to try again. I think I'm going to try to draw it by hand. So I have to do exactly a right angle to the, wow, that was bad. Let me try again. Okay. Does that look like a right angle? Yeah, that looks better. Okay, if I have exactly a right angle right here, boom, boom. And now I'm going to do it again. I'm going to go a right angle to this radius. Boom, boom. Ooh, cool picture. They're intersecting. That's cool. All right, so this is, we'll call this FG. So that's a chord, and we're going to call this one HQ, headquarters. All right, so let's go back and see what we have here. So we have if, I don't know, I guess it's the video. I can take extra time. Sorry, you guys. Okay, so if we have CB, and it says equidistant, so I'm going to use the distance instead of the shapes. So distance is a number. So I'm going to say if CB equals CA, they're both equal to 2, right? They're equally distant from the center point. So this is 2 away and this is 2 away. And if chords are equidistant from the center, and you have to know that they mean perpendicular. And assume perpendicular, because the way we measure distance is the perpendicular distance. If you have a line and a point, and I want to say how far away is that point from that line, you need to measure it at a right angle. Otherwise, you could get an infinite number of answers. Okay, so I'll just leave that there. If CB is equal to CA, and we're assuming that they're perpendicular, then this theorem says that FG is, chord FG is congruent to chord HQ. That's what that says. Chord FG is the same length, and that makes sense because it's the same distance away from the center. The converse, anyone want to try it? Converse. If two chords are congruent, then they are equidistant from the center. Two chords are congruent, then they're equidistant from the center. Cool. All these fun things you never knew about chords, and now you know. Ooh, let's do another math problem. What's this say? It says if EF is equal to EG. So that's like what we just kind of did here. So EF, let's just randomly say that it's, I don't know, 3. Should we say it's 3? Let me see. We'll mark it. EF is the same as EG. Okay, if EF is the same as EG and CD is 24. Okay, CD is, what's AB? This is the same distance away. So if you know that theorem, then you know the answer. AB is 24. Done. Don't have to show any work. Okay, I know that they're the same distance away from the center, so I know that they're the same length. Ooh, this one's the most important. If a diameter is perpendicular to a chord, and you know what? If it's a diameter or radius, if a radius or diameter, actually any segment that contains the center, is perpendicular to a chord, then it bisects the chord. Okay, this is pretty cool. Let's see how this works. If a diameter is perpendicular to a chord, then it bisects a chord. So I can start with any chord I want on here. I'm going to do chord AB. Chord A, B. Chords are line segments whose endpoints are on the circle. Okay, and then I need the center of my circle, which I'm going to say is about there. And we'll call this circle D. And I'm going to, right here. Okay, and I need it to be a perfect right angle with it. It has to be perpendicular. So I'm gonna use this diameter or this radius, and I am going to make it perpendicular. And you can kind of see it, right? When I did it, when it lined up as a right angle, you could see that this side and this side are about the same. So it's kind of a cool thing. So if diameter DM, sorry, if line DM or line segment DM, I mean, it doesn't have to even be a diameter or radius. As long as it contains the center of the circle and it's perpendicular, that's cutting the chord in half. So if line segment DM is perpendicular to the chord AB, then we're allowed to say in a picture like this that AM is congruent. It's bisected. They're the same. To line segment MB. Okay. D is the center. This first one has to be containing the center. If it doesn't contain the center, and we can't assume that. Cool. You can do the converse on your own. Here's another math problem. If the measure of, hey, I've seen this one, but now it's asking me for something else. So if the measure of arc AB is 43, and we know that AC is equal to DF, find the measure of arc AC. Okay, well, that's here. And we just learned, we kind of assumed this before, but now we know for a fact, here's a right angle, which means that these two are the same. And we already knew these were 2. Okay, we also know that this is 43. We also know that if the chords are congruent, then the arcs are congruent. So we actually know a lot in this picture. I wonder if we could find that. Interesting. Okay, so the measure of arc AC is simply, you could use the arc addition postulate, and it's just double. So the measure of arc AC is 43 plus 43, which is 86. Done. You don't really have a lot of work to show on these, but you do kind of have to have a sense of the theorems that we're talking about today. Here is the most fun problem and the last problem we're going to do. So here's a problem, circle P. We know that QS is 9. It's a little bit awkward to label this, which is why they put it up here. You can put the 9 right here if you want. We want to find the value of X. How are we going to do that? Well, let's start with what we just know. We know we have a part of a diameter, part of a radius, and it's perpendicular to this chord. So what do we know about QR and RS? They're the same. So if the whole thing is 9, how much for each part? It's half. So 4.5. 4.5 for here, and 4.5 for here. Okay, I'm going to get rid of this 9 because it's kind of in the way. I split it in half. I knew it was 9 from up here, but half of it here and half of it here, because it's a perpendicular, I know it's cutting it in half. All right, now what? I want to find X. This one's a little tricky. Do you see the right angle? Watch and learn. Ha 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 ha. All right, what shape did I just draw? Okay, you see this shape in here is a right triangle. What is this? This is a radius, isn't it? Isn't this also a radius? So these are both radii. Okay, which means that if I can solve this right triangle for this hypotenuse, and find out what r is, the radius, that's the same as x. So if I can find this hypotenuse, I've figured out this problem. So let's do it. Let's do it. I'm gonna redraw this right triangle over here. Basically, I don't need the circle anymore. I just need to remember how to solve right triangles. I'm taking this one out of the, moving it out there. I'm going to take the measurements with it. That's 4.5. This is 1.9. This is what I'm trying to figure out. X and R are the same because they're both radii. Okay, and then, hey, look, it's a right triangle theorem. A squared plus B squared equals C squared. Okay, I'm going to do 1.9 squared and 4.5 squared. That will be whatever my answer is, squared. I'm going to square root both sides, and I'm not going to mess around with this stuff on calc. I don't want to do 1.9 times 1.9. What I'm going to do now that I'm older and know how to use a calculator, I'm going to go type all of this into Desmos, and then I'm going to hit equals. And it's going to tell me approximately how much this is. So square root of x squared in geometry class is x. In algebra, you have to make sure if you want the positive or negative square root. Okay, let's go type this into Desmos. Let's go, let's go. 1.9 squared. So I'm going to start with the square root. I'm going to use my parentheses. I'm going to do 1.9 quantity squared. I actually don't want it inside the parentheses. So I'll close my bracket, parentheses squared plus parentheses 4.5, close parentheses squared. Done. That's my answer, 4.88-ish. Okay, and this is a rounded answer. And if it doesn't tell you how much to round to, I don't know, go 2-3 decimals. I think SAT is 3 decimals. So let's round to 3 decimals, 4.885. 4.885. That's it. X is about 4.885. Woo! And if it was a special right triangle, they'd probably want an exact answer. Be good. Keep learning. Work hard. Bye.